What's going on, everybody? This is going to be the first notes video in Advanced Chemistry over Chapter 3, which is going to be about equilibriums. Now, I had to answer a couple of questions yesterday. I haven't actually gotten around to checking those results, and this is coming so close after it that I assume most of you haven't answered anyway. But we're going to start with a little bit of a thought exercise and a little bit of an introduction. So our section 1 is like, what is equilibrium? What is this stuff that we're talking about? So let's use a thought exercise from last chapter. Let's say that you add a teaspoon of sugar to a big glass of water, a big old glass, like, we're talking like one of those gigantic Yeti cups of water. And you stir and you stir and stir until the sugar completely disappears. Has the sugar dissolved? And then you take the same glass of water, but now you keep adding until you are 100% sure that you have hit the saturation point of the glass. You know for a fact, you can't determine why, but you know that you could not get any more sugar into it. And then you add a little bit of more sugar, so it just sinks to the bottom and doesn't dissolve. Is that sugar, saying it doesn't dissolve as in it's like staying at the bottom, is that sugar dissolving? Well, you might be able to guess because of the fact that I changed my wording a little bit on that last one, that this is not going to work out exactly how you would expect it to. Your instincts probably tell you that, okay, well, this one the sugar is dissolving, and this one the sugar is not dissolving, because you just said it sank to the bottom. You might think that, but you probably won't be shocked to learn out that that is wrong. The first example is dissolving. You are still dissolving it whenever you make it disappear in the water, but so is the sugar that you put in the saturated solution. So your question might be, well, Diamond, did you lie to us? Because we know you do that sometimes, and I do that occasionally whenever we haven't gotten to the point yet. But I didn't actually lie to you. There's just a little bit more that we have to talk about. So there's actually more to do with solutions and saturation than just what we talked about. We talked about like forming the solutions and describing the solutions and the chemistry involved in it and the process to make them. But there's a little bit more. Saturation is the point at which no more solute can be dissolved in a given solvent. Well, if that's the case, how can the solvent be dissolving, or how could the solute be dissolving? The reason is because saturation and solutions in general are usually examples of what is called dynamic equilibriums. So this is kind of going to be our introduction to equilibriums here. An equilibrium is just a state in which a system, where there is no observable changes as time passes. You can think of it kind of the state has equalized. It is equaling out. It can be static, like this picture of the rock over here. This would be a static equilibrium. I would joke and say that this is like a video, but some of you might stare at it in hopes that there's an Easter egg or something that's going to happen. But no, this is just a picture of people that stacking rocks is like a pastime that some people do. They go out in nature and they stack rocks like this. And this is a static equilibrium. That's static because theoretically, unless it fell apart right at the moment that this ended, or this picture was taken, that this is completely stationary, and it is balanced out in its stationary state. But it could also be dynamic, like this old guy walking up a down escalator. He is technically staying in place. He is at the same position. His hand is barely moving up the railing as he's walking. But he is staying still, even though he's still moving. So this would be dynamic equilibrium, and this would be static equilibrium. They're both the same thing. They're both something staying in place. This one just is requiring effort and requiring a movement, and is having this flow of him stepping up and the stairs moving down, and that cycle is happening at an even rate, and so that's dynamic equilibrium. So now we can go back to our saturated sugar example. How is the sugar at the bottom dissolving? Well, that's because when you hit the saturation point, there is no more sugar allowed to be dissolved in that liquid. It cannot be dissolved anymore. However, what can happen, and what does actually happen, in fact, turn down my volume a little bit, I think I'm getting a little bit too loud, is that once you hit the saturation point, some of the sugar that's inside of that solution is going to turn back into a solid. And at the exact same rate that sugar that's aqueous, that's dissolved, turns into a solid, some of that solid sugar is going to turn into aqueous sugar. It's going to be like if I can go back here, it's going to be like our old guy here. It's going to loop around, even though he is moving upwards, even though some of that sugar would go, the aqueous sugar would dissolve back into the liquid would then or sorry, even though some of that aqueous sugar would turn back into a solid, that solid is then going to reform and make more crystals. That's the stairs coming back down. It's a two-part cycle, and it's just looping and looping and looping. So that equal exchange of aqueous sugar to non-dissolved solid sugar is exactly the same rate. It's happening at the same speed, so that is a dynamic equilibrium. It is an equilibrium that is not staying completely still. Now, when something reaches that equilibrium point, that should mean that the concentrations of whatever you're dealing with should level off. So we've got a graph, for example, over here. You can think of the red line as the reactants because you start with a whole bunch of it, and the blue line as the products because you start with a lot less of it. As the red line drops, as you lose reactants, you're going to be forming products. So our red line slowly goes down and our blue line kind of increases upwards. And you'll notice that as they progress, it's steeper here than it is right here. This actually explains for some of you that did like how much sugar could you get into really, really hot water in the sweet tea lab. You might have realized that it took a lot longer for it to dissolve the closer you got to that saturation point. Well, this is why. The rate of the reaction, or how much it can actually change, levels off and slows down as you get closer. We'll talk a lot more detail about that a little bit later on. But you can see that eventually they reach a point where this is starting to get flat. And after this point, you can kind of see that the line would probably be pretty close to flat. And even though those concentrations have leveled off, they are approaching their equilibrium, and it would be dynamic because there would still be exchange as long as it is a reaction that can go both directions. So notice, though, that this graph does not have our reactants disappear. This graph, the reactants go away, but then they flatten off somewhere around this 0.1 concentration, 0.1 molarity, and we started with 0.25, and then this one starts at 0 and ends up at 0.15. Now, in this case, this would be a very, very simple reaction. This would be a one-to-one reaction because we started with 0.25, and we've ended up with a total of 0.25 concentration units, but it's now split across of our products down here and our reactants that came from up here. So you might think that's weird because shouldn't the reaction just kind of end? Like, shouldn't it keep going to make the reaction end? But just think about that in your real life experience. For every lab you've ever done in my class or in any other classes, does it ever work perfectly? We always talk about how, like, you can't, you have % error and % yield and stuff like that because you know that things are just not going to work out. They're not going to work as effectively or as perfectly as you want them to. Well, part of the reason for that is because as this reaction goes, as it kind of starts reacting and reacting and reacting, there's going to be a point where that stuff is not going to want to keep dissolving. If you think of it like the sugar, you can only get so much sugar in water. You can only get so much salt in water. By that same kind of idea, you can only get so much of a reactant to react. It doesn't matter if you use exactly the two ratios that you think should give you a product. One of them is probably going to have some stuff left over. You're probably not going to form a complete product. This is actually why, if you've ever noticed that in a lot of the reactions we'll do, we might care about the reaction between substance A and substance B. Substance A will very carefully measure it, and we'll say we have 25 grams of substance A. And then for substance B, we'll be like, and then fill like half of a beaker with it. The reason for that is because we want to make sure that we have enough of one of the reactants that it makes it keep going and it can get as much of the reaction to happen as possible. When you have a very small amount of it, it'll actually prevent the reaction from going all the way if you have very small amounts of both of them especially. So now that hopefully gives you a little bit of a basic understanding of what equilibrium is. It's the idea of something being equal or exchanging at an equal rate. It can be static, like rocks being balanced, or it can be like an old guy running up an escalator. Both of them involve something staying at the same place, but they just involve a change in whether or not they're staying still, like a static equilibrium, or a dynamic equilibrium, like chemical equilibriums, where, for example, sugar at the bottom of a glass that doesn't seem to be dissolving is actually exchanging equally between the solid and the aqueous ions. They're just kind of making this nice circle pattern of crystallizing out, then dissolving back, crystallizing out, dissolving back, that causes them to still be at equilibrium. So the stuff that we're going to talk about this chapter, and this is our last slide, this is just to give you an idea. We're going to talk about general chemical equilibriums. Then we've got two specific ones we're going to talk about. We're going to talk about acid and base equilibriums, solution equilibriums, and then, even though this isn't going to be the last thing we'll talk about, we'll actually probably talk about this in section 3. We're going to talk about one of the fundamental principles of chemistry that you have been kind of doing stuff that involves that principle for probably all of your chemistry experience. But apparently you guys haven't learned about it. It's what I got from you guys earlier when I asked some of you in class about it. But it is one of my favorite things to talk about. It's a very weird concept, but we'll talk about that principle, and you can start maybe getting some ideas of how some of the chemistry that actual chemists do, or some of the labs that we've done, why they've been structured the way that they've been structured. So I hope that makes you guys feel a little bit better on equilibrium. I know I got a little bit rambly there. It is kind of early in the morning, so my voice is a little scratchy, and I did just finish making these notes. So I hope you guys have a great rest of your day. I hope you guys have an awesome week, and I hope to see/hear from you soon.